Good afternoon. I'm going to talk to you today about some simple methods for synthesizing linkages to achieve particular motions. And the things we're going to look at are these. Quick graphical methods for designing or synthesizing a grashof non-quick return crank rocker. Secondly, a link moved through two positions, with that link being the rocker of a grashof 4-bar. The third thing, move a link through two positions, but with the link being the coupler of a grashof 4-bar. In fact, that might turn out not to be a grashof, as we'll see, but it will be a 4-bar. And moving a link through three positions, with that link being the coupler of a 4-bar linkage, which may or may not be grashof. And finally, an alternate solution to the link through three positions. And all of these will be done using only a compass and a straight edge. Okay? Let's look first at the grashof non-quick return crank and rocker. Now, for this example, you would normally start with the desired position or two positions of the output rocker. And you might think of this as the classical windshield wiper mechanism design example, where this link, labeled AB, will ultimately carry the windshield wiper blade. Now, that windshield wiper blade might in fact be on an extension of that link up there, but we don't care about that for the moment. All we care about is finding the locations of the pivots for the other links. And the other links are going to be the coupler, which will connect point B, or B prime, to the crank, which may turn out to be over here someplace, and the crank in turn coupled to the ground. Now, this is going to be one of our ground pivots, so I may as well mark it as such right now and show that that will be pivoted to the paper. Now, the first thing I need to do is to determine the arc through which this will go. And since that light pencil doesn't show up very well, I'll darken it in with a pen. Freehand. Now, that arc is the true path of point B as it rocks about pivot A down below. But the displacement of that is the straight line distance between the two. So I want to draw the straight line connecting B, B prime. And I'm now going to extend that line in any convenient direction, which, because of the position on the paper, is to the left. I could as well solve this by moving that line to the right, and I'll get a mirror image solution to the one that we're about to come up with. Now, this line extended, this chord, BB prime, is going to represent the line of the coupler and also the crank in the two positions of the crank rocker, which will place the rocker, and let's label this link 4, which it will end up being, in each of its extreme positions. You should remember from the lectures that the extreme position of a rocker, or any link in a 4-bar linkage, is defined as that position which occurs when the two links connecting it to the other ground are in line, either extended or overlapped. Now, in order to find out where the crank should be, I'm going to have to make a guess. I can pick any point along this line, literally any point, and have a potential solution. I'm going to cheat a little bit because I've already solved the problem and I have a model that I'm going to show you when we're done. So I'm going to put the pivot in the place that matches the model. But I can put the point that I'm about to describe literally anywhere along this line. I'm going to choose that point right there. That point that I just chose, somewhat at random along that line, is going to be the other fixed pivot. In this case, it will be for the crank, link 2. Now, link 2 is going to swing in an arc about that center, and when it goes through 180 degrees, I want it to drive this from B to B prime. And when it goes through the other 180 degrees, to drive it from B prime to B. The next question is, how long should that crank be? Well, if the crank is going to be in this position when rocker is at B, and in this position when rocker is at B prime, then the total distance from this position of the crank to this position of the crank must be the same as the distance B to B prime. Easiest way to find that out is to do the old bisection trick as originally demonstrated by Euclid or somebody or other, to find the midpoint of that line, which I will do like so, and that gives me the proper length of the crank. So I'll set my compass to that length, which is half of BB prime, and swing this circle over here. That represents the crank radius. I'll draw the crank in like so, call that link 2. Now all I have left to do is connect up with the connecting rod, as it's sometimes called, or a better name for it is the coupler, because it couples one end of the linkage to the other. And we can get a little fancier here and show some shape to link 4, which I didn't show before. And that's the solution right there. Link 1, which is not yet numbered, is simply the line of centers. It is the piece of paper, and it's the distance between the two fixed pivots. Now, the only remaining question is that in fact a grashof linkage? It may or may not be, depending upon where I happen to choose that pivot. As a general rule, the further away I move in either direction from this mess over here, the more likely it will be that it will be a grashof linkage. But I must check that condition, and I can check that very quickly by first determining which is the shortest and which is the longest of this set of links. Let's look for the longest. The shortest is pretty obvious. The longest is either this line of centers or the coupler, and obviously it is the line of centers, link 1. Let's so label it right here. So why don't I just lay out link 1 down here as a reference. So link 1, this is L. That is, it's the longest link. And I will now lay out link 2 immediately adjacent to it, because, whoops, you may or should remember that the grashof condition says that the sum of the shortest and the longest link must be less than the sum of the other two for it to be a grashof, and I would like this to be a grashof. So there's the sum of the S and the L, and we'll compare that now just graphically to the sum of the other two. There's one of the other two, and if I start that there and add to it the length of the other one, I see I'm home free, because call that link P arbitrarily and call that link Q arbitrarily, and you can see that S plus L is less than P plus Q. So, eureka! It is a grashof linkage, and the problem is solved. And as I said before, I've made up a little cardboard version of this, which I will now place on top of our diagram and show you that in fact it does move link 4 through or to the two positions originally desired. There's the center line of link 4, and that's in its extreme position when these two links are collinear right here. And when I rotate that around such that link 2 and 3 are again collinear but overlapped, we find that link 4 is there. And if I get this tack out of my way so I can swing it through its full rotation, you can see that I can keep going around with link 2, rotating in one direction only, and it will move link 4 back and forth, thus providing the kind of motion we said we wanted at the outset, which is a windshield wiper mechanism, if you will. I'll put a nail in it so I can move it a little more easily. And the motor is on, my hand is the motor on link 2, turning it continuously. And if I try to turn that at constant speed, without stubbing the toe here, then I think you can see that link 4 is moving back and forth at about the same time interval. And that's my non-quick return grashof crank rocker. Okay. So, we've taken care of number 1 here. Synthesis of a grashof non-quick return crank rocker. The next one we want to look at is the link through 2 positions, with the link being the rocker. And let's say that we want to have the link be at some time in position AB, that is our link, let's say, and later on A prime B prime. Now, we're no longer talking about a windshield wiper mechanism here. A simple example of an application for this sort of thing might be a production machine in which you are going to move the workpiece into a workstation so that perhaps a rivet can be placed into a hole and rivet 2 pieces together, and then moved over to another workstation where some other operation can be performed, or the part can be ejected or moved down to the next station in the assembly line. So the positions AB and A prime B prime, which are 2 different locations of the same link at different times, are totally dictated by your desires in the machine design problem that you're dealing with. What we want to do now is find out how we can drive that link through those 2 positions. Well, there are a couple of ways to go about this, and the first way I'm going to show you is noted down here on the label. I'm going to consider this link to be the rocker of a crank rocker. Now, again, it might turn out to be a rocker if it's a non-grashof, and I may not care in this instance. But at least this will be a rocking link that I'm going to design right now. And to do that, I want to find the displacement track of each end of the link. And I'll do them one at a time so that they don't get too many lines in the way here. Point A can go along any path its little heart desires. I don't really care. I just care that it start out life here and end up over there. And on the average, its path will be this straight line. That is properly called the displacement of point A. So I draw the displacement track of point A, which is the straight line connecting its 2 positions. And now I'm going to construct the perpendicular bisector of that displacement track, which is very easily done with the compass. And I will draw that line now and extend it in some convenient direction. Now, presumably, the direction that I'm heading, namely south here, is one in which I have some framework of the machine available for attachment of the appropriate pivots and whatnot. Or I may not even know where the machine frame is yet. It may be that early in the design, and I don't care, in which case I can go in any direction. Now I'm going to draw the displacement track of the other end of the link, which is point B. And I'm going to construct the perpendicular bisector of that. And it is the bisector as well as being perpendicular. It's going to cut that line in half. And I will draw that and extend it in such direction that it intersects the other perpendicular bisector, which I've already drawn. Now this intersection down here is called the rotopole. And it is something of a significant point, at least in respect to this problem, because, as I think will be obvious to you already, if I put my compass at the rotopole as a center, set it to the distance rotopole A, and swing that arc, you can see that it goes through both A and A prime. It has to. Any point on the perpendicular bisector taken as a center will, by definition, go through both A and A prime. That one happens to go pretty close through B, but that's coincidental. This point is also on the perpendicular bisector of the line BB prime. Therefore, it will serve as a center around which any arc struck with that radius, or the arc struck with the radius rotopole B, will go through both B and B prime. So if I use this as a center then, for the rotation of this link, and I'm going to now draw some meat around that link which started out life as only AB, line AB, I'm going to add some meat to it such that it comes down and picks up this pivot, which I will now attach to the frame, which I hope is in the right place. If it's not, I'll have to solve the problem a little differently, but let's assume that I have some machine frame available down there to attach to. So I'll drill the hole, put the pin in, and what I've so far created is a single link which will, when rotated through a particular angle, this being the particular angle right here, move the line AB into the position A prime, B prime. Alright, what do I do next? I only have one link, and I was looking for a 4-bar linkage. So I've got still some work to do. Well, the work I have left to do, we've really already done. Because if I now go back to step 1 here and create a grashof non-quick return crank rocker, for which this is the rocker, right here, then I'll be all set. I'll show you how to do that very quickly. It'll be a repeat of what we just did before. I'm going to choose some quite arbitrary radius here, whatever seems nice, and I'm going to find the intersection of that radius with any line, any radial line on this link, and I'll choose the line that goes from the rotopole center to point A, for reasons which will be obvious in a moment. I just want to darken that radius in so you can see it. And why did I choose the line through A? Because then I can find out where it is over here without a lot of hassle. It's got to be the line that goes to A prime. So that point right there, let's give them some names. Let's call this C and call that C prime. It's the same point, moved over. And that point is going to serve as a point of attachment for my coupler. Now remember that I chose its location arbitrarily. It can be at any radius, it can be at any angle with respect to this link. I can add meat to the link and put it over here if I like. And that would be dictated by the framework of the machine that I had to attach to. Now the problem has been reduced to the one that we did before. I extend the chord CC prime in any convenient direction, and let's say that I have some room over to the left, and I'm going to now choose an arbitrary point on that line, let's say there, and I'm going to let that be, at least tentatively, the center of my crank. Remember, this is so far only the rocker. I'm now trying to find the crank and the coupler to go with it. Well, as we saw before, the length of the crank will be, if I want no quick return, will be exactly equal to half the distance CC prime. And it looks like it's that line right there. There's the perpendicular bisector, the CC prime, right here. So I'm going to take half the distance CC prime, and you could just as well do this with a scale if you have one handy. But I'm going to be stubborn and do it with just a compass and a straight edge here. And that radius, CC prime divided by 2, when struck around the center over here, gives me the location of the crank. Now, since I have drawn this link in the leftmost position, then to be consistent, I've got to draw the crank in the leftmost position over here. So I will put the crank in over here. This is link 2. I now must couple the crank up to the rocker with the coupler. And the coupler length is already defined, since it has to connect this pin joint to this pin joint. Now, it may or may not be easy for you to see at this point, but it will be easier when I show you the model in a moment, that when I rotate this crank over to here 180 degrees, point C is going to end up at C prime. And if C ends up at C prime, and C is part of the same link that A and B is part of, A will end up at A prime, B at B prime. And that's much more easily seen with a model. So here is that model. There is my link A, B, and C, and that's going to be pivoted down here at the rotopole. So I'll put a pin in there, and I'm going to have to grab that ground link someplace else so it doesn't rotate, so I'll just pin it down right there. And I've deliberately put this onto the paper in the position wherein the crank and the coupler are exactly overlapped. So from that position, if I rotate in either direction, the link number 4, let's number the links, call that 4, call that 3, call that 2, call that 1. I guess the black pen doesn't show up well on dark green on the television. You'll have to take my word for it that that's number 3. And you can see that that's going to rotate link 4 into the 2 desired positions. So what have we done? We first of all, having decided we wanted this line to be here and later there, found the rotopole, which is the one and only one center which will allow that line to rotate from this into that position. That's a unique solution. Having found that and created this larger link 4, there's 4 right here, that's 3, that's 2. Then we went back to the grashof non-quick return synthesis procedure, picked an arbitrary point C, found out where it ended up, cut that distance in half, picked a point somewhat at random, found the circle at that radius about this center, which is the track of that pivot, and then connected the dots, coupler and crank. We still have to check, is it grashof? I can tell by the fact that this little thing worked that it is, but if you wish to check the condition, obviously making a cardboard model will tell you whether it's grashof or not. But you can save yourself some work if you first look at that inequality. And that is a solution to the problem of putting a link through 2 positions, with that link being the rocker. Takes care of number 2. Now we want to move the link through 2 positions, but have that link end up being the coupler in the final 4-bar linkage. And to do that, we'll take a slightly different problem here, which again has a line defined as A1, B1 in this case, later on to be in position A2, B2. And we want now to create a linkage which will move it as the coupler, as link 3, not as link 4. That's the difference here. The technique is very similar to the one we just went through. I'm first going to find the displacement tracks of each end of the link. And notice I'm connecting like letters here. B1 to B2, A1 to A2. Now I'm going to find the perpendicular bisectors of each of these lines. In this case, the perpendicular bisector of A1, A2. Which is along here. And by the same technique, I'm going to find the perpendicular bisector of B1, B2. I'm deliberately not going to show them intersecting, though obviously they will, because this time I don't want to use the rotopole. That's the difference between this solution and the other. The rotopole is right there where they intersect. And if I wish to do the solution just previously described, namely the link as the coupler, then I would be interested in that rotopole. But I'm not going to use it because I want this to be the coupler. I think at this point it would be useful to put a little meat around these links so we can recognize them amid all the other lines that are beginning to appear on this thing. I'll show that one dotted because that's the other position of the link. Now, I can literally take any point on the perpendicular bisector of the line A1, A2, and as previously demonstrated, any point on that line will satisfy the constraint that an arc struck from that point through A1 will also go through A2, right? A1, A2. And in like fashion, any point on the perpendicular bisector of B1, B2 will both go through B2 and B1. That's just plain geometry. So I can literally pick any point whatsoever on each of those perpendicular bisectors, and I have a potential pivot for my other links. So I'm going to pick a point right there, very arbitrarily, just as a guess. And since that is on the perpendicular bisector of A2, A1, then I'm going to create a link that connects that point that I just chose somewhat arbitrarily with one of the A's. It belongs to the A because it's on the bisector of the A1, A2 line. And that's going to be one of my ground pivots. So I'll show that getting fixed down to the paper right there. I said I wanted this link to be the coupler, which means in my numbering system it will be link 3, and I'll arbitrarily call this one link 4. Now I'm going to do the same procedure on the other perpendicular bisector, namely the one that bisects B1, B2, and I'm going to pick any point at all, and I'm going to connect that. Since that belongs to the B1, B2 line, I'm going to connect that up with the B end of things. And since I chose to connect to the A1 before, that means I should connect to the B1 here, because that whole mess is going to go over here to A2, B2 when I rotate it. This point that I've chosen somewhat arbitrarily on the perpendicular bisector becomes the other fixed pivot. I think you can see that if I did in fact pass this link, this will be link 2, if I did pass link 2 underneath link 4 as I've happened to show it, I'm going to be in a little trouble getting across that pivot. But I can get out of that pickle by either pivoting this up onto another surface which is above the paper, or I can just flip the links over. And I've chosen to flip the links over here. And I will show you the cardboard version of this right now. Unfortunately, these pretty colors don't show up very well in black and white, but we'll have to live with that. I'm sticking that pin in fairly close to the center that I chose at random, as best I can find it in the dark here. And this one, since I've got to pass the other link over, I'll have to use a thumbtack so I can lift that link over. And this is link 3, which doesn't show up too well. And if I rotate either one of these as an input, and can do it without stubbing toes and so on, I'll find that if I rotate through the appropriate angle, this link 3, which is my AB line, goes from this position over to this position later. Now this might be a Dempster-Dumpster kind of mechanism, where this is the position in which it's carried on the truck, and this is the position in which it is picked up, used to pick up the dumpster that's sitting on the ground, and then picks it up and flips it over to dump its contents into the truck, or something of that sort. So here we have started out with the definition of 2 positions of a link that we desired, and found some combination of 4 links that will put it through those 2 positions. And you can get some quite unusual differences in position accommodated by this technique, more so than by the one using the rotopole with the link as the rocker, a 4th link in the system. All right, let's move on to the next one. And the next one is, just did that, move the link through 3 positions as the coupler. Here are 3 positions. And they could be any 3 positions that you desire. I've chosen them here to try and keep the solution on this small sheet of paper, but I don't mean to imply that the relative positions of these are significant to the solution of the problem. I've labeled them A1, B1, and later that same line is in position A2, B2, and later that same line is in position A3, B3. To do this, we simply extend the same technique that we just used for the 2-position synthesis, namely connect the dots A1 to A2, but we have another one to connect also, in this case A2 to A3. Now I'm going to find the perpendicular bisectors of each of those lines. Perpendicular bisector is right there, and I'll extend it in some arbitrary direction in which I have paper to draw it on. And again, in the real world, you presumably would be looking to extend it in a direction wherein you had something to attach to. Because the intersection now of these 2 perpendicular bisectors, both of which are associated with the A end of the link, is again a rotopole. And I'll call it rotopole A because it is for the A end of the link. And again, from basic plane geometry, that point, that rotopole, is the unique solution to the problem of where is the center of an arc which will go through 3 points, A1, A2, and A3. So that's the only point which I can use to drive point A from this position to this position to this position in pure rotation. Okay, do the same thing for B. I'm going to have a displacement track from B1 to B2, and another one from B2 to B3, and I've got to do the perpendicular bisector of each of those. And their intersection will give me another rotopole, which will be the rotopole B right there. And that point, that rotopole B, is the center of the arc, which will contain B1, B2, and B3. Now all I have to do is connect the dots. Connect the rotopole of A with one of the A positions, like so. Connect the rotopole of B with one of the B positions. Put some meat on this link, A1, B1, so it looks a little bit more like a link instead of just a line. Of course, a line is sufficient to define a link in 2 dimensions. And we'll show these pivots attached down to ground in some fashion. And there you go. There's your linkage. Link 2, link 3, link 4, link 1. And that will drive this A1, B1 line to the 3 desired positions. And here it is in indelible permanent cardboard. If I have the right end, that one looks like the ground link. So I will pin that down there and show it here in A1, B1. Later on, got a little argument going with the pivots here. I'll have to put a headless pivot in there so that I can get this link over it. And it will go to A2, B2 now, and in turn go to A3, B3. Now it's quite possible that the technique just demonstrated may not work in a given case. It may turn out that you cannot move these links through all of the motion necessary to get from the first to the last position without disassembling them, because it might happen that there is a limiting position of links being collinear in between, depending upon the particular relative positions of the 3 link positions that you started out trying to solve for. If that be the case, then there is a possible way out, which is the next item to be taken up here. You wouldn't be able to discern whether or not you had a good solution until after you've gone through all of this construction, found the 2 rotopoles, and then either built the cardboard model, or worse yet, built the metal final product and found it didn't work. Another good argument for cardboard models. Or you could alternatively check with a compass to see whether it will go through. And I'll try and show you how to do that here, since you might not want to take the trouble to build a cardboard model in each case. Link 3 is by definition this long, the distance from A1 to B1. A1 travels along this arc. I'm trying to find the proper arc here. There's so many lines now. I better check that. Make sure I'm on the right track here. That's it. Happens to go through B1 also. So that's the arc A, let's say, of the point A. And it's constrained to go through that arc if it's pivoted on link 2. And here's the arc B, which I guess I never drew before. And that goes, I've got a little error in there, but that's all right. You can see these quickly become a forest of lines, and a little bit hard to keep track of what's going on. Now, if link 3 is at all times connected to point A at one end and to point B at the other, then I can, with my compass, follow the path of length 3 by keeping one point of the compass on the arc associated with A and one point on the arc associated with B. And as long as I can succeed in doing that, I got lost there. Let's try that again. We start over here, and I've got to keep the point of the compass on the B arc and the pencil of the compass on the A arc. There we go. There we are. I got crossed over right here before. So the point of the compass ends up at B3 and the lead ends up at A3. And as long as I can keep those points of the compass in contact with those two arcs throughout the entire motion, then I know it will go through. Probably your best bet is to build a cardboard model, and then you'll be sure whether it goes through the motions that you are after or not. Okay, that takes care of the specific solution for the length through 3 positions as the coupler. And notice that that was a unique solution because we used the rotopoles, and there is only one rotopole for the path of the A end of the link and another unique rotopole for the B end, so there was not any optional solution. And as I mentioned, you may run into trouble with it not being able to go through the entire motion. What do you do then? Well, what you do then is this last item. You try to design it to go through 3 positions with alternate attachment points. And I'll show you how to do that right now. I'll have to give you a peek at the solution here in order to do this, but it's all right. What I'm going to do now is enlarge the link in any direction and to any shape that I desire to include 2 other points. Now these points are chosen largely at random. I'll call them C and D. And they have a particular relationship within the same link. This is all one solid hunk of material, and it's a rigid link, so therefore the line CD has some particular geometric relationship to the line AB, and that relationship will obtain in all of these 3 positions. So C2, D2 will be there, and C3, D3 will be there. I'll just show them dotted as outlined here. The outer shape of the link doesn't really matter. So what have I done? I've changed the problem to one in which I was trying to move the line A1, B1 through the successive positions to a problem of trying to move the line C1, D1 through successive positions. And since that is a different line, I'm going to get a slightly different solution. The method is exactly the same. I'm going to do the track of C1 to C2 and the track of C2 to C3. I'm going to take the perpendicular bisectors of those 2 tracks, and I'm going to find the rotopole of C. I guess I need a longer radius for this one than that. So there's a perpendicular bisector of the line C1, C2. And there's a perpendicular bisector of the line C2, C3. Extend them till they intersect. That's the rotopole for C. And do the same technique for D. D1 to D2 is that line. D2 to D3 is that line. Get the perpendicular bisectors. find their intersection. Right there and right there. There's the rotopole of D. And presto, there it is. All I have to do is connect the dots. C1 to the rotopole of C, D1 to the rotopole of D. Ground the rotopoles by pinning them to the ground plane. Paper is link 1, call that link 2, that's link 3, that's link 4. There's my 4-bar, probably a double rocker. I haven't even bothered to check the grashof. You don't really care in this instance whether it's grashof because you're trying to make it rock through these 3 particular positions and probably don't want it to go any further, which you can guarantee by putting in some stops. Looks like some error has crept in. Those pivots aren't quite in the same place on my model as they are on my drawing, but let's see how it works. There's the linkage attached at C and D. Notice the pivots are right there now. And A and B are just holes punched in the paper. And we'll move that over there. And again, I've got to put a little flathead tack in there because this has to pass over as it did before. There it is in the 2nd position, and there it is in the 3rd position. Now, if you recall, the other linkage looked a lot like this, but the rotopoles are in slightly different locations. And if I had moved line CD into much different juxtaposition to line AB, I might have moved the rotopoles to a different location. So this technique will come in handy when you either have gotten yourself into the fix of not being able to go through the entire motion with your solution, or perhaps the rotopoles of your first solution are not in a convenient location to attach to the frame, and you'd like to move them to another place. So that completes the set that I wanted to talk about today, showing you a basic non-quick return grashof crank rocker synthesis method and 2 methods of 2-position synthesis and 2 very similar methods of 3-position synthesis.